Physics Notes, Unit 22, Part B, Magnetism. What is the source of all magnetism? The movement of electric charge, which leads to this situation, discovered by Hans Christian Ørsted in about 1920. They say, I think he discovered this by accident. I'll talk a little bit more about that. But the discovery is this, that magnetic fields surround current-carrying wires. So why would a magnetic field surround a current-carrying wire? Well, because it goes back to the basic principle. Because moving charges create magnetic fields. And that's what current in a wire is, moving charges, moving electrons, moving through. You can think of them moving straight through the wire. And we think of positive charge instead of negative charge. Doesn't matter, but we're going to use the convention of positive flow. This red arrow here represents current flowing in a wire. And we have what's called the right-hand rule to figure out the direction of a magnetic field, which are circular. I mentioned that in the previous notes. The direction is given by the fingers when using the right-hand rule. Now, I'm going to use the convention from our book. They call this the RHR2, right-hand rule number 2. I'm going to do these in opposite order that they do them in the book. Right-hand rule number 2, or just usually it's called right-hand rule. But once again, these magnetic fields are circular. In these two diagrams here they look purple or blue, that represents a magnetic field around this wire when there's current flowing through the wire. And the right hand, basically the fingers show you the circular pattern of the right-hand rule. So you take your hand and you stick out your thumb and you curl your fingers, your right hand, and you wrap your fingers around the wire to represent the magnetic field, and your thumb points in the direction that the current's flowing in the wire, the conventional current, from positive towards negative. So I have two different diagrams here. The one on the right, same thing, but we have these circles that represent magnetism. And the magnetic fields are full. They're not just distinct lines. These lines represent the magnetic field, but it does get weaker the further from the wire you get, stronger by the wire. But it fills all of space around the wire. And they're circular. We could draw millions of circles, but enough there to show the diagram in both cases. And you can detect these. It's said that he determined, or he was one day, Ørsted was, I don't know what he was doing in the lab. He had current on a wire, and he happened to have a compass needle nearby, and he saw the compass needle going crazy. And that's how he discovered it. I think it was by accident. So you can use compass needles to detect these magnetic fields, or iron filings. I think you'll see a picture of that later in the notes. Now, we don't want to really draw the diagrams like this because it's too complicated and it can be a little confusing, possibly. So we have a convention that's in every book. Pretty much every book, every scientist pretty much follows this particular convention. When we draw or represent magnetic fields, yeah, we can draw these circles, but we have the convention that an X means into the page or towards the floor. And a dot means out of the page or towards the ceiling. So I usually put a circle around, a lot of books put a circle around that. So this means into the page, I'll add here, toward floor in general. It almost always means towards the floor. For our purposes, it always does means towards the floor. Or this one means out of the page or toward the sky. Toward the sky or towards the ceiling. I don't like to use the word up because that can be misinterpreted because we also have towards the top of the page. So we have to think in 3 dimensions here, but we have our limitations with a 2-dimensional piece of paper. So to alleviate misconceptions, we have these conventions that then will be helpful in getting our correct orientation on a flat piece of paper. So for example, starting off with the right-hand rule, if I were to lay a wire on the paper now, if this represents a wire, it represents a wire with current going this way, towards the top of the page. So that arrow represents towards the top of the page. Right? So this is a wire. That represents a wire. That red line. Now, and this is current towards top of page. toward top of page. Now I'm going to represent the magnetic field with X's and dots. And I'm going to switch colors. I'll use the blue. So here it is. If that wire was laying on your table, the magnetic field would surround it. It'd go underneath the table, around it, circle around the top. So this is how it would look. This would represent, and here the smaller circles represent the field getting weaker with distance. Let me explain this. Okay, let me finish drawing this. These are all supposed to be the same size on this side. And then they get smaller. Once again, smaller circles represent weakening magnetic field. So these directions represent tangents to those circles. So if the magnetic field is circling around this wire, if the wire is laying on your table, if you were to grab it with your right hand, your thumb pointing towards the top of the page, and you had to pick up this wire, your fingers from your right hand would poke into the page on the right hand side of the paper, through the tabletop, through your paper, if you could poke through the table. But that would be the tangential direction to a circle. When your fingers would go in there, they would circle underneath the wire. So underneath the wire, the magnetic field would be to the left, tangentially, directly underneath the wire. And then it would circle back around and it would tangentially, that's once again, those dots on the left-hand side would be tangents where your fingers would come back out of your table, if you could poke through the table, and that'd be tangential directions to a circle. So they represent tangents to circles at those points of tangency. All right, let me give you the other example, the wire on the right over there. Okay, let me draw the wire. So in that case, here's a wire with current going this way. All right, and up here in this diagram, so we have all these circles, but now if we put the wire on a piece of paper, all right, and you were to grab it with your right hand, your thumb pointing to the left, all right, now we're going to draw the tangential directions to those circles, and it would be like this. X's, that's where your fingers would have to poke into the paper, and then weakening with distance. And then on the other side, obviously, then it would have to be your fingers would come back out over here with weakening strength the further you get. We're going to practice this some more. But a lot of these problems that we'll be doing are going to require three-dimensional thinking and then being able to represent that clearly on a two-dimensional piece of paper. So this helps us do that. And all books basically follow this convention, including our OpenStax book. Okay, so other things to consider now and in the future as well. If you take a wire, a straight wire, and these blue arrows represent magnetic field surrounding the wire. If you take the wire and you start to coil up the wire, what happens is geometrically the magnetic field intensifies in the center of that wire. That's going to be important later on. Or over here, here's what's called electromagnet. If you take a wire and just coil it around, coil it around, coil it around, okay, that long orientation there is called a solenoid. I'll write that down later on. And we have an soft iron nail right here. And what happens is if you put current through that wire by closing this switch right here, what happens is you get a strong magnetic field because of the looping wire, strong magnetic field due to the current in the wire, which then will magnetize that soft iron, because soft iron can be magnetized very easily. The domains of the electron orbits become big. That nail becomes magnetized, and then it will pick up other magnetic things like paper clips and iron filings. If you had iron filings or anything basically ferromagnetic, it would pick up. Then if you open the switch, it would drop it. It would drop the iron items. So that's what they use to make a magnet that can be turned on and off very quickly for applications in switches. And well, one famous example is like junkyards where they pick up old iron cars. They have a huge electromagnet on the end of a rope on a crane, and they can turn it on to pick up a car and move it around. I'm not sure they really do that much. Or they can do this with separating out old iron pieces from junk. You can have an electromagnet. So those are some applications. And a magnet that can be turned on and off is very useful. All right, but now calculating the magnetic field strength around a wire. And we call them long straight wires. We're going to stick with straight wires for now, then we'll go back to curling the wires to intensify, because once again, intensifying something is always useful. But right now we're going to stick with just a straight wire. Okay, so everything we've drawn so far was just qualitative, just visual, like how strong a field is. The field lines give you a feel for how strong it is. You know, the closer together the field lines are, the stronger the field. But now we're going to calculate the exact intensity numerically of one field compared to another field. Very useful to get a quantitative number. And the equation is B, magnetic field strength, is equal to mu. Let me switch back to red. The equation is B equals mu 0 over 2 pi times I over R. All right, and once again, it is a vector, but the vectors are going to be pretty much limited to the tangents to the circle, because the circle is a changing direction as it circles around. We'll practice this. But mu 0 is given. It's the permeability of free space. You're going to be actually verifying that, I believe, in one of your labs. But the accepted value is 4 pi times 10 to the negative 7th newtons per amp squared. And if you take, that's mu 0. Permeability of free space. But if you take mu 0 and you divide by 2 pi, which is useful in the equation that we're dealing with over here, mu 0 over 2 pi has a value of 2 times 10 to the negative 7th, because if you take mu 0 divided by 2 pi, the pi cancels out. So we're going to be using this number right here, 2 times 10 to the negative 7th, as our shortcut in these calculations. Okay. Once again, all the standard units. Current is in amps, the distance from the wires in meters, and then the given units for mu 0, and then the magnetic field strength comes out in Teslas. So we can start off straightforward application. We're going to plug into that equation I have up there, calculate the magnetic field strength, B, at a distance of 2.5 centimeters from a wire carrying that much current. So mu 0 over 2 pi is the 2 times 10 to the negative 7th. So I always use that. That's my mu 0 over 2 pi times I, which is the current, 6 amps. That's good. 6.0. Over how far I am. It's 0.025 meters from the wire. Now that 2 times 10 to the negative 7th goes upstairs only in the numerator. You multiply that by the 6, and you divide by the 0.025, and you end up with 4.8 times 10 to the negative 5th Teslas. That's how strong the magnetic field is at that distance from the wire. That's the strength. And the direction would be tangent to any circle that you draw at that particular location. That would be the direction, is the tangent of the circle. We don't need to worry about direction yet, but we will eventually here. For example, now the directional things come into play with this application. Magnetic force on a charged particle moving through a magnetic field. Okay, so here's where the rubber meets the road. The electric charges, electrons and protons, moving through electric fields, magnetic fields, experience a force. When they move through a field, or a wire is in the field, they are deflected at right angles. At right angles. At right angles. Now, the vector geometry of this, I'm not going to get into all the details, but suffice it to say, they're at right angles. Bottom line, for example, if you can even imagine right now, you're sitting in a room where you're facing the north wall. You're facing a north wall. In that room is a magnetic field. Fills the room. You can't feel it. You can sense it. You can detect it with compasses. You can't feel it with your body. You don't have any sensors in your body to feel it. But you know a compass anywhere in your room will point straight north. So if you're in that room right now, if you're in a room where there's a magnet, well, you're in a room. You're in somewhere. And if you face north, there's a magnetic field for sure facing straight north. That'd be the direction of the magnetic field. If you had an electron that tried to come from your left to the right, from your left, which basically if you're facing north would be come from the west going east. All right, as that electron or proton, either one, let's pick a proton right now because the proton is the conventional. You have a proton going from west to east towards the right, trying to go through that magnetic field. It would feel a force, according to this rule right here, F equals QVB. It's a cross product. It's actually F equals QV cross B. I took off the cross product right now because cross product means sine of theta. But all the problems we're going to be doing, unless you're told otherwise, we're going to use the angle of 90. In other words, if you have a proton going from your left to right, from west to east, all right, and the magnetic field is towards the north, that's perpendicular. So we're going to do all perpendicular, sine of 90, that'll drop off, but it is a cross product. But F is the force, Q is the charge, in this case was the proton, right? And it's the charge of a proton is always given. It's 1.60 times 10 to the negative 19th coulombs. We learned that earlier in unit 18, I believe. V is the velocity of the proton as it goes towards the east. B is the magnetic field strength. In this case, it would be the magnetic field strength of the Earth, which I forget what it is. You can look it up. I'll give you some numbers here in a little bit. You can calculate the force on that charge. And the force, though, is going to be perpendicular. And here's where the three-dimensionality comes in. And you think of, well, it's going to be the right-hand rule number 1. It's a little bit more involved than right-hand rule number 2. And what you got to think of is X, Y, Z, 3 dimensions. X, Y, Z, 3 dimensions. So we got to think in 3 dimensions, and we got to represent that on a 2-dimensional piece of paper. And that's where the challenge comes in. We're all challenged by this. It's nobody's fault, but we have to be able to think 3-dimensionally, which takes practice, and represent it on a 2-dimensional piece of paper. So here we go. Right-hand rule number 1. So the basic diagram here, this diagram hopefully helps you. All right. There's probably about 10 different variations on the right-hand rule. I'm going to do the one that's consistent with our book, the Open Stacks. This is not the one I normally use, so hopefully I can keep it straight. But there's, like I say, many different variations, but here it is. Okay, it's called the right-hand rule, not the left-hand rule. So you put your hand out flat, like a palm, and this kind of shows you the 3-dimensionality of this. And you have, instead of curling your fingers now, your fingers are going to point in the direction of the magnetic field. For example, in the one I was just using, and kind of lines up real nice, V is the velocity of the particle of a positive particle, so in this case a proton. So if I put my hand flat out with my palm facing the ceiling, my fingers facing towards north, and my thumb facing to the right, it's towards the east, which is exactly what this diagram is. The direction your palm is facing, you think of an arrow coming out of your palm is straight up. So in other words, if a proton tried to come through this room right now, doing what I just said, coming from my left to right, from west to east, traveling towards the east, this velocity vector is towards the east. All 3 of these are vectors, and they're all perpendicular to each other. We say they're mutually perpendicular. The angles are all 90 degrees. If it wasn't 90, you could put in sine of 80. That would reduce the force a little bit. But the force on a proton that tried to come through this room would actually make it try to curve upward toward the ceiling. There'd be a force that tries to make the electron or the proton go towards the ceiling. All right? That would be the direction of the force. Calculating the force is pretty easy. You just do F equals QVB, sine 90. Once again, into or towards the floor is going to be an X. Out of, towards the ceiling, will be a dot. So here's a couple diagrams you're going to be faced with in the homework. And I'm going to show you how the more conventional way to draw these. Basically, because you'll need to be able to draw these diagrams. But once you get used to them, they're all very similar. All the diagrams, when you simplify the diagrams, are going to look like this. They're going to have a circle. In this case, the circle, now and this is example A. It says B is in or towards the floor. That's towards the floor. So I'm going to draw that as an X. So this is how I always do it with a circle. Okay. So B is towards the floor. All right. In the example I just did with the proton, V is to the right. And then this diagram over here on the left, okay, actually, this one's a little bit different than the one I was just doing with the room, okay, because here the force would be towards the ceiling. This diagram here is a new diagram. It's not. This one would be like a magnetic field going towards the floor, not towards the front wall. but the proton is still going to the right. Proton is going to the right, so I'm giving you 4 new problems here that are different than this one. This is the first diagram. By the way, in this, let me go back to this one on the left. If I were to draw the final answer for that one on my paper, because I wouldn't want to draw it like this on the paper. On the paper, I would draw, here would be my representation of this diagram over here, where I have V to the right, okay, and in this case, B is towards the front of the room. That's towards the north. So that would be conventionally towards the north. V is towards the east. So the answer here would have been a dot, or F is towards the ceiling. So this diagram right here is consistent with the diagram I have here on the book, and it would be consistent with, or on the paper, consistent with a proton going towards the east, the magnetic field going towards the north. Because on a piece of paper, flat piece of paper, this direction is always north, and this direction is always east. Toward the left is west, and towards the bottom of the paper is south. So this diagram right here is consistent with this right-hand rule scenario with that situation I told you about the proton. This is a new scenario now. This would be like a magnetic field towards the floor, which is not the Earth's magnetic field. You have to have some kind of external agent creating a magnetic field towards the floor. So now if we have a magnetic field towards the floor and the velocity is toward the right, now what you have to do is you have to take your fingers and point them towards the floor, because your fingers always point in the direction of B, the magnetic field. But my thumb still points to the right. So if I do that now in the room I'm sitting in, or the chair I'm sitting in, if I point my fingers towards the floor and my thumb to the right, my palm faces the front of the room. So now in this scenario, part A, the answers to the problem, so the question would be, here's the scenario, give me the answer. The answer is I need to have F. F is going to be this way. That's my answer, so I'm going to do it in blue. And the one over here, the F was the answer, was towards the ceiling. You're not always looking for F. In these first two, you are looking for F. But bottom line is, every diagram I draw will be a circle with 2 arrows that are perpendicular. Let me do several more, because it takes a little bit to get used to this. Do 3 more at least here. So I always start by drawing a circle. In this case, it has the velocity this way. That's called, I'm going to call that V, but it's V negative. It's the velocity of a negative particle. So that's a little monkey wrench here. And it says B is up. Once again, I don't like up. What that means here, because up could mean towards the ceiling. It doesn't mean that in this diagram. They would draw dots here if they meant up. What they mean here is the magnetic field is towards the top of the page. That's what we mean when it draws a diagram like this with arrows pointing towards the top of the page. If the page is laying flat on the table, that particular word up there, which I try to never use, this is just the example, it means towards the front of the room. So you have to be very clear, what does it up mean there? Well, here we're saying it's towards the front of the room. So if you were to treat this as a positive particle, you'd want your thumb pointing to the left, your thumb pointing towards the left, as you're looking at your flat tabletop. Your thumb pointing towards the left, okay, and your fingers pointing towards the front of the room, towards the top of the page. So in that case, your palm would face the floor, and towards the floor is an X. That would be true for a positive particle. What you'd fill in the circle here, because what we're looking for in this particular diagram is what do you put in the circle for the force. Well, it'd be an X towards the floor for a positive particle, but here's the deal. You've reversed the answer for a negative particle, so that's a real monkey wrench here. Oh boy. So the answer there is, for my force, the force on the electron would be towards the ceiling. In that case, the force would be towards the floor for a proton. Let's practice some more, and you'll start to get the knack for this. Every diagram is going to be a circle with 2 perpendicular arrows. I'm going to keep practicing. So, in this third case, C, you have X, you have a particle. So you have to forget the ones you just did, because the answer is going to be different. You have V here, the velocity of, we're going to assume it's positive unless you're told otherwise. And you have the force, there's 3 vectors, F, V, and B. So now we have F and V, we want to get B. I'll tell you right away, that's what's given. You're given the force to the right, the velocity towards the floor. So this starts to simplify this. The answer is either towards the top of the page or towards the bottom of the page. So those are the 2 possible answers. I'll put them. So the answer is either this, okay, I'll erase that, or the answer is this. Okay, so we're limited to only 2 answers because it's got to be 2 perpendicular. It's got to be perpendicular to F. Okay, so if you don't know, if you don't know anything, if you're short on time, just 50-50 chance of getting it right. If you're short on time, just guess one of those two. It's got to be one of those two, but let's get it right. So V is your thumb. Okay, so you have to have your thumb pointing towards the floor. If you're looking at a flat tabletop, so you have to have your thumb pointing towards the floor. So it's going to feel maybe a little awkward. Okay, what you have to have, and your palm has to face towards the right. So if you take your thumb towards the floor, okay, I have to kind of twist my arm. So if I start with my palm twisting, if I start with my, once again, I'm using my palm, but I'm starting with my palm facing the floor, but that's not right. I want my thumb facing the floor. I just keep my hand really stiff. I keep my right hand really stiff, like this. But I'm going to have my fingers, well, the fingers are what are going to determine the answer. But I have to do what it says here. I have to have my thumb pointing towards the floor and the palm of my hand facing towards the right. And if I do that, my fingers point towards the front of the room. So that's the answer. The answer is, because here I'm looking for the fingers, which way my fingers point, and they point towards the front of the room, and that's the answer for B. All right, because I was looking for B in this example, not F or V. F and V were given. Do another one. A lot of practice here. So the diagram is, all right, so I start with a circle, and I have B towards the ceiling, and I have F towards the bottom of the page, south. So once again, my final answer is either this way for V, I'll erase that, or it's this way for V. It's one of those two answers. I'm going to put the B up here in it, so it's a little bit out of the way more. Okay, because B is towards the ceiling. So I take my rigid right hand, and my fingers have to point towards the ceiling. All right, and the palm of my hand has to face towards the back of the room. The palm of my hand has to face towards the back of the room. So if I do that in this case, my fingers have to point towards the ceiling. Palm of my hand, think of an arrow sticking out the palm of my hand towards the back of the room. Then my thumb automatically points to the right. So the answer is this way for the velocity. That's the way the positive particle would be moving to get that particular scenario. So you can start to see a pattern here, I hope. All right, that's practicing the right-hand rule. We'll practice a little bit more here. How about this? Charged particle traveling south in a particle accelerator, kind of like out at Fermilab or at CERN in France and Switzerland. They have a big particle accelerator out there now. The old one was the smaller one at Fermilab. They still do labs out there. And Professor Carnio, who's your lab professor, works out there. That's Fermilab. Anyway, it says we have a charged particle moving south, experiences a force. So I'm going to draw the diagram. Let me go back to red. Okay, so draw the diagram to get my orientation here. It says a particle, so I always start by drawing a circle. We have a proton. It's moving south. Okay, south is towards the bottom of the page. So the velocity here is towards the south. It says it has a force that's east. So in this circle, I want to have B. The question is B towards the ceiling or towards the floor? Do I put a dot or an X? So you always put a dot or an X in that circle. Well, let's practice the right-hand rule one more time here. So I have to have my thumb pointing towards the back of the room, okay? But I have to have the palm of my hand facing, the palm of my hand has to face to the right. So I basically have to, I'm going to drop my hand to my side. Okay, so I'm going to put my arm like straight down, with my thumb pointing towards the back of the room, my palm facing to the right towards the east. It turns out then that forces my fingers to go towards the floor. So the answer for my fingers here is towards the floor. So that's my directional answer. That's what wasn't given to me. I'm going to put that in blue. So if I ask for the direction, it's towards the floor for that magnetic field. But now I'm going to calculate the strength of that magnetic field. That's the easy part. Well, once you get used to the right-hand rule, that's pretty fast as well. But now I want to calculate the force. F equals Q VB. All right. So I plugged the numbers in. They gave us the force, 4 times 10 to the negative 12 newtons. The charge, it's a proton. Look that up or remember it. 1.60 times 10 to the negative 19. It's 10 to the negative 19 there. Times the given velocity, 2 times 10 to the 7th. Times b, the only unknown. So you divide both sides by the 1.60 and by the 2 times 10 to the 7th. And you end up with the magnetic field strength of 1.25 teslas towards the floor. Okay, so part B, it says, what if the particle were an electron? Well, the thing is, if the particle were an electron, the diagram would change. Okay, well, the force is still, it says if the force is still the same and the velocity is still the same, to make this work for an electron, bottom line is you just change your answer. So instead of a magnetic field towards the floor, you would need a magnetic field towards the ceiling. And if you look at the math here, if you plug in F equals QVB, it's all the same numbers. It's 4 times 10 to the negative 12th equals 1.6 times 10 to the negative 19th times the velocity of 2 times 10 to the 7th. It's all the same. That's 2 times 10 to the 7th times B. So you really wouldn't even need to plug that all in. It comes up to be the same answer. You need the same strength, because they're the same charge, you need the same strength magnetic field. Okay, but this would be towards the ceiling or toward the sky. All right. Same answer. But now it gets a little bit more difficult. Part C. Part C. Calculate the radius of the circle it will be deflected into. All right, well, what happens is, because the force is at right angles, it deflects it into a curved path, into a circular path, such that F sub C, well, I'll put it this way, F sub E equals F sub C. And if you go back, well, F sub E is QVB, that's what we're just doing. QVB is the electrical force, or the magnetic, well, no, that should be F sub M, not F sub E. F sub M, the magnetic force, is QVB equals centripetal force, this goes way back, mv squared over r. mv squared over r. All right? So that's an r down here at the bottom. The other ones are v's. Well, if you solve this for r, you get r equals mv squared over, you switch around, over QVB. And one of the v's cancel, so this equation becomes r equals mv over qb. I would circle that and put a star by it, because that's going to come up in the homework. You don't need to recreate all that. It's going to have a problem like this. It says calculate the radius in this particular magnetic field for this particular particle moving at this speed with this mass and charge. So you use the same equation. So that's going to be an important equation. That comes up a lot when you get a charged particle in a magnetic field. What is the radius of the circle? So bottom line, I'm going to do this for the, let's do it for the proton. You can do it for the proton and for the electron. Let's just do it for the proton. It'll be a different radius for the, it's going to be a different radius. It's a different radius for each because they have different masses now. Same magnetic field. But if I want to find the radius for the proton, r sub p, it's just going to be plugging in mass of the proton, which is what? 1.67 times 10 to the negative 27th. That's the mass. So now we're going to get a different number because of different mass for the electron, which we're not going to do, times the velocity, 2 times 10 to the 7th, divided by q, 1.60 times 10 to the negative 19th, times the magnetic field, which is 1.25. So, like I say, radius of the proton, you plug that all in, the radius of the circle that the proton will be deflected into, and it will be uniform circular motion, 0.17 meters. And that's part C. And like I say, if you want to do that for the electron, it'd be a smaller mass. Everything else is the same, so you're going to get a smaller radius. It's going to be a different radius circle, even though the magnetic field is the same to satisfy the conditions in part A and B, but the radius of the circle would be different because of the different masses. Now, an interesting application of this is with a device called a mass spectrometer. And they have what's called mass spectroscopy, where they can determine elements that are present based on their mass and based on these principles of deflection, because as we just showed, or I talked about, the electron would actually be deflected into a smaller radius circle that has less mass. Here we have two things that are similar in mass, two oxygen atoms that are accelerated in a, well, they're shot at a certain speed through an electric field, which we'll talk about in a little bit here. But this over here represents the circular path they're deflected into because of the force. All right, the force is going to be at perpendicular right angles to the motion, and when the force is perpendicular to the motion, that is classic centripetal force. It is a classic then circle of motion if you have a uniform force in that uniform field. And this shows you those pathways that these two different masses take. Bigger mass will take a bigger path. So you can separate isotopes according to their mass using a mass spectrometer. So the question here is, in part A, what is their separation distance? So we're going to basically just do what we just did in the previous problem. In part A, the radius of the path is, what was the equation? mv over qb. mv over qb. So we're going to figure out the radius of the path for number 1, for the 16, the 16, and it says the mass of the 16, oxygen 16, is 2.66 times 10 to the negative 26. It says the velocity, I'll plug these all in, hang on. So I did the math there. I plugged in, the mass of that isotope times its velocity divided by its charge, singly ionized. In the homework, I think it says there's one that's double or triple ionized. It has a triple charge, I think. So you got to multiply this number by 3 to get the total charge, and then times the magnetic field strength, 1.25. So the radius comes out to be 0.67, but it's a semicircle. If you go in here and circle around, so this is the diameter of the circle, and the radius is 0.67, so twice the radius is the diameter, 1.34 meters. So this red circle right here is the distance away from the entry point that it exits, 1.34 meters. Now we have to do that for the 18 as well, but it has a bigger mass, so we got to figure out the mass of that first. Let me do that. So I did all that math over here, and there's some shortcuts you could take, but it tells you in the problem that the ratio of the masses of isotope 16 to 18 is 16 to 18. And if the mass of the isotope 16 is 2.66 times 10 to the negative 26th over the mass of 18 equals the ratio of 16 to 18. If you cross multiply and divide, basically you get the mass of 18 is 2.99 times 10 to the negative 26 kilograms. It's basically you take the mass of number 16 and multiply by 18/16, like by 9/8. It's a little bit more massive. Okay? Then you plug it into the same radius equation. All you've done is change the mass to 2.99 instead of 2.66. Multiply that all out, so the radius of the circle for the heavier isotope is bigger. And the diameter then is bigger, 1.50. So this distance right here, is 1.50 meters. But we're looking for this distance right here. This little distance right there is what we're looking for. Well, that's going to be the big distance, 1.50. It's going to be 1.50 minus the shorter radius or diameter, which is the 1.34. So the separation there, we're going to call that x. All right. So x, the separation distance, the answer that we're looking for is 0.16 meters. That's how far the two beams are apart when they come out or hit the target. If there's a target over here, that's how far apart. That little distance there is 16 centimeters, 0.16 meters. Okay, one more thing to do here. Part B, it's kind of a review problem. It says calculate the electric field in the velocity selector. So this thing over here is called the velocity selector. And what has to be true on the far left here is there's an electric field here. This is a little bit of a review. Good review. And then there's the magnetic field force, magnetic force, F equals QVB. So once again here, what we have is, well, we have a particle that's going through straight, and we're ignoring gravity here. It's inconsequential if you calculate the force of gravity. But we want F sub E, the electric force, equal to the magnetic force, which is the new concept we're dealing with. Well, Fe, if you go back a couple of units, back to unit 18 or 19, E equals F over Q. So F, electric force, equals EQ. That was way back from unit 18. So this is EQ. Magnetic force we just have is QVB. Well, the Q's cancel out, and you get E equals VB. Or if you just solve for V, let me scroll down here a little bit. This is going to be an important equation. The velocity coming through that straight path, the V is going to be E over B. That's going to come in handy in the homework. Very handy. So write that down, star it. That's the velocity when you go through these parallel plates where there's a magnetic field trying to deflect the particle towards the bottom of the page, and the electric field is trying to deflect the particle towards the top of the page, and they cancel. So the particle goes straight. The net force is 0, and towards the top, towards the bottom of the page, so it goes straight to the right with a constant velocity. It comes out with that particular velocity. That's how they select that particular velocity. If you set those plates so those particular electric and magnetic, well, the magnetic field is set to whatever it is, 1.25 Teslas, and the E field. Well, they're asking you to find the E field here. It says calculate the electric field between those plates for these particular conditions. If the magnetic field over there is also 1.25 Teslas. Because that 1.25 Teslas is not making it curve right now. It wants to make it curve, but it won't until it gets through those two parallel plates that are keeping it from curving. So I just plug into that for part B. I gave you the velocity. The velocity is what? 5.0 times 10 to the 6th. So we have 5.0 times 10 to the 6th is the velocity. That's 10 to the 6th. Equals the E field over the 1.25 Tesla magnetic field. And if you do the math there, you end up with an electric field of 6.3 times 10 to the 6th newtons per coulomb, or volts per meter would be an equivalent unit. All right, so we've figured out the force on a charged particle going through a magnetic field, and we've practiced the right-hand rule. We'll practice that some more, and then we'll move on to the force in part C of these notes, the force on a wire in a magnetic field. And to remind you once more, though, before we do that, moving charges have magnetic fields. Moving charges have magnetic fields. Moving charges in a wire, a straight wire, creates a magnetic field around the wire that circles. And when we have conflicting magnetic fields, a charged particle that's moving with a circular magnetic field through a linear magnetic field, like in this case, that creates that magnetic deflecting force that is a centripetal force.